All right. It's just a demonstration of the STM, uh, the STM 32 board using the accelerometer that comes with the board right here. Configured using the SPI communication protocol uh, with sampling rates of 100 hertz. So, wanted to demonstrate the you can get it to configure. You can configure it to display out the information of the accelerometer. And I'm just using a Java program uh, program by a certain YouTuber. It's a free software just to display the actual readings. So um, that's just moving it up and down. And change the see there it changes the amplitude depending on the orientation that you have it. So you can see it reads positive and negative values depending on uh, uh, the the orientation of the axis, uh, uh, reference to the gravity of the Earth. So the green one is the z-axis. You see it's negative since I have the board turned upside down. If I turn the right side up, you'll see the green will shoot up to a positive number. I believe this one is the y-axis. So have it turned up and turn down. It's the negative sign, and then the x-axis. That's still x-axis. Oh yeah. Red is the X. I got it confused with the Z. And then turn it up. Yep. So just gonna run through the codes here. How I got it to configure everything. Um, I'll actually first show the. This is based off the reference manual. Uh, the application notes by TI. But I'm sorry, not by TI, by ST microcontroller. Uh, it's the AN3393. And on page 12, it has a startup sequence and how you can get how just tells you kind of like the procedure to go about reading the value. But the actual code implementation takes a little bit more effort to get it going. Just bring this one. So the approach to making to doing this, I use MATLAB, STM hardware, uh, hardware, hardware support program via Sumilink to program this. Um, well, to mainly just set up all the peripherals and kind of interface some of the things and also do some function callings because I had to do some custom. I have some custom header files and program files that MATLAB calls up functions that actually are ran and and, uh, and it is used to extract all those datas. So go up the system. So pretty much what it is there's a uh, initiation initiation block here. So that just pretty much initiates should initiate the SPI communication with the accelerometer. Uh, this is the header file for it. Let me pull up the code. All right. So in the header files, I just defined some of uh, the commonly used or some just a couple of the registers that I definitely use and a couple other registers and stuff that I'll probably use in the near future to do certain things with the accelerometer. I have a couple of functions here. The SPR write, SPR read, uh, accelerometer, accel init, which is called in this function block. Um, and then read Excel that actually extracts the X, Y, and Z uh, numbers from the accelerometer, and then the function that actually returns the X, Y, and Z number. So let's start from the top here. I had to declare a couple different variables here. This is just so that whenever I run my initiation codes for the SPI communication, just want to have a kind of uh, a variable that tells me whether I ran it once, and I only want to run it once. And then this variable, uh, I guess once we go down, we'll kind of explain what it is. But just know that there's these six variable here. So the way the accelerometer transmit the values of the x, y, and z coordinates, it's a 16-bit integer value, but but it's separated by per axis is separated by two registers, 8-bit registers. Um, so this data out XL, uh, the out X XL is the lower 8 part of the 16-bit, and then the XH is the upper part of the 16-bit. So the way that it works out in the code is I just scroll down here real quick. Once I extract it, I have to actually bit shift the upper 8 bits by 8, and then add the lower part to it so it can create that 16-bit values. Um, so let me actually start here when it calls the accel int function. So like I say, just want to run this configuration just once. Here it's enables the timer for I believe it is for uh, yes, it's for peripheral A uh, peripheral A pins on the microcontroller. And then oh, no, I'm sorry. This is actually peripheral D because of they're the LEDs. So it will be these ones here. It enables the peripheral D clock, and then it sets Uh, it says the alternative no, it says it resets the 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 pins to a default state, and then writes the four pins as GPIO uh, output, and then sets the pins to low, and then this one enables the peripheral. Let me see here. This is okay. Okay. Wow. This code here. Uh, oh yes, this is a chip select. This is chip select code. Just bear with me. I took the initialization code for the SPI from a guy uh, 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 on get 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 it GitHub, and I haven't gone back and kind of polished it up and just make sure everything makes sense. But like it says here, yeah, the GPIOE clock enables it, uh, and then it resets the beats, the it resets the ports, and then sets the port as output, and then since the SPI communication is at idle is high, it sets the chip select uh, port to high, and then here it enables the GPIO-A clock peripheral. Um, then enables the SPI1 peripheral clock in the microcontroller, the APB to ENR. So these are just different clock buses, and they well, I won't go into details with it, but yeah. And then here it sets the alternative mode of the actual port. It resets it and then sets it to alternative mode as SPI. So let me actually pull this one up here. Yeah, so this one. Just quickly show you. Yeah. So here it sets PA5 uh, 6 7. Oh, now that I think about it, I'm kind of double setting it because I've already set it here. I've already set it here. Yeah, so I don't necessarily have to call that function again. Actually, matter of fact, all these, I don't have to call it up because it's already set in the using it's already set using the CubeMX STM CubeMX software. So the CubeMX software just allows you to visually configure all the pins. There is menus. You can actually go and go a long way with it. Configure like the baud rate, set up interrupt uh, and interrupts, set up different all the different parameters and stuff. So really, that function I didn't have to necessarily call. And even looking at it now, uh, this function here uh, for the SPI, I believe I've already set it up. Oh no! Oh no! 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 Okay, I think I know what's going on now. Okay. Well, no, yeah, I've already set it up, I believe. Yeah. Um, Let me just track back here. Well, I'll have to go back and look at it again. What I'll do, since it's already a working code, I will bring everything back. Okay. So here it just sets up the SPI communication. Uh, uh, don't no need to go further in detail with it, because it just, you set it up once and that's it really. So here I using yeah, uh so this one, when the guy, whoever the guy's previous code actually use a different chipset. This chip here on the older HTM board, on the older STM boards, there was uh, there was this chip here. Yeah, so as you can see here, it's uh, let me actually open up the data sheet for it. Okay. Mm-hmm. Section application notes for it. But so the chip that he's working with is this chip here. You see it's a lot more rectangular. The chip that I'm working with is this one here. It's a square version of it. If I scroll all the way down, just bear with me. Okay. Yeah, you see it's a square chip. Actually tells you what orientations you can go. Uh, so yeah, so with that one, I believe its registers were different. So I once I reference use this reference manual, it told me exactly what I needed to do. So on page 12 of this reference manual tells me exactly what I need to do for my specific ship, and got it to work fine. So where were we at? So I don't necessarily need these for loops. Actually, take it out because that was I was running this code here, and that was unnecessary to use that. So yeah, this the setup code, the initiation code is not that bad. And then this the guy which I referenced, this SPI code from. Let me actually just show you his Git GitHub. So it's this fella here, FCI. He made a STM F4 bare metal uh, example files, project files and stuff. And on the SPI, he interfaced with the accelerometer that was built inside the board. So yeah, so that's his code right there, and kind of use that to help me set up the SPI communication. So thanks for that guy for doing that. Uh, so yeah, so that's the initiation, and let's go back here to my lab. So now, oh, so now there's this external interrupt uh, uh, subroutine that goes on. So here, uh, this code here enables the X, Y, and Z readings, and then it sets the read speed or the update speed to 100 hertz, and then you can enable an interrupt pins that will be driven by the 100 hertz signal, so that if you uh, so that because it's connected to uh, pin it's connected to pin P3 on the microcontroller. I can show here too on the schematic. So you can see here pin E3 uh, is this is the chip select. Oh, I'm so sorry. No, pin E0. Oh my gosh, pin E0 is is the interrupt one. Uh, the, that's the chip select GPIO out. This one, the external interrupt, is connected to P0. So because if the P0 is driven, it drives that 100 hertz signal, creates a 100 hertz uh, interrupt subroutine that can then be used uh, to cut up to actually extract the readings once it is ready. So here I cut up these read Excel functions, and the read Excel functions. Let's go back here. What this one does is so it retrieves the status of the SPI pin. So this is pretty much like it's uh, pretty much you're uh, verifying that this this new data that you received is this data uh, this data that you're about to read is actually new data. So what happens is once you read the data, uh, pin not pin on the status register. Let me go back here. On the status register of the I was having a hard time finding this. Oh, it's late too. So oh yes. So here it tells you X, Y, and Z axis new data available. Default is 0. Uh, new 0, a new data set is not available yet. And then it sets it at 1 if a new data set is available. So what I'm doing is just uh, reassuring that I'm reading new data sets. And it's also part of the instructions here. You want to check if there's a new data set. Now there's another uh, in the same register you can check the position 7 of the register. So here to see if any data was overwritten. So as long as you read those data, uh, uh, as long as you read those data with the speed at which the interrupt is being generated, uh, your your data will never be overwritten. So you always validate that you've read the new data. So here I'm just reassuring, and what it does is it extracts the the high and the low of 8-bit values of the total 16-bit value of the x, y, and z uh, coordinate, and it saves it. See, there, pulls it from the this register and it saves it uh, to those value. And these SPR read and SPR write registers are just show you here. So this pulls for SPR write, it pulls down the chip select pin. So tell it, hey, I'm ready to write some data um, into your registers. And there's just a uh, uh, framing. There's a way that you gotta frame it. So you take your register address, you shift it 8 places, and then your data is on the lower part of the 16-bit frame. So yeah, so they're pretty much the same here. For reading, uh, you also sorry mm, here for reading. Oh yeah, here for reading is pretty much the same thing. Uh, where you set up your frames and then you send it the address that you want to read from. Okay, so now here, um, so okay, yeah, let me go back to here. So here, there, there's this X, Y, and Z uh, function call, and this is actually returns you values of your X, Y, and Z coordinates. So, so uh, I actually was having some trouble and stuff at the beginning because like I say, it the data package sends is a two's complement 16-bit data that for your coordinates that comes out and stuff. So I was kind of having trouble at first because I'd actually typecast this as unsigned 16-bit integers, and I uh, upon converting it, it gave me a value from 0 to uh, 65,000, I believe it's 600 and 500 something. So pretty much give me the full from 0 to 2 to the power of 16 number. But because it's two's complement, it has to be signed integers. So I kind of spent like a couple of hours trying to like troubleshoot it and see why exactly it was giving me that. And I was actually thinking of like doing it two's complement conversion, but then you know kind of took a break and watched a couple of videos about two's complement, and then it just kind of clicked. Um, and I realized that I can just call it as signed integers, and the software C itself is gonna do the conversion for me. So that was uh, that was interesting. But I mean, it was a learning curve. So then from then these values get sent out to this uh, telemetry converter, which interfaces the SPI data to USART. So what this one does is it puts it in the frame, in the package frame that uh, you can send it to USART, and can display it in the terminal. And I mean, this is a code that I've been kind of recycling. Just been coming here and changing my string character size, changing my what is this again? My specifiers for the actual variables that I wanna uh, send to USART, and it's quite self-explanatory. So it just creates a buffer and then tells the USART how big of how big of the string characters that I'm sending, and then here I'm just using a USART block from USART block uh, from from the STM hardware support package, and yeah, that is uh, that is pretty much it right there, and that's pretty much the chunk of everything. MATLAB really just pulls all the strings in, do all the code generation for me. So let me see here. Let's view code. So it takes all the code here, and you can kind of can click on it. Show you the chunks of the code that are used to the each block uh, generates, and it generates headers and code files for me, initiates the peripherals for me, and do all those stuff. Now there's a SPI block here in MATLAB that I could have used, but for I tried to get it to work, but it was quite complicated. So I just resorted to doing uh, the user uh, the user the custom user codes, and then just cut up functions. Uh, Actually, what happens is you include the header files that you create in MATLAB here, this function block, and then you cut up the function uses code ceval, and MATLAB just uh, creates the code for you. And if you had any arguments that goes along with the code, you'll just put comma and then put the argument there. So it's pretty intuitive and straight. Well, I won't say straightforward. You have to spend for a beginner. You have to spend a little bit of time uh, uh, working with the MATLAB environment, and kind of being a little bit being familiarized with its features and uh, what's it called, the functionality, how to do different things and stuff to get your code going and working and stuff. But that was that was pretty much my uh, uh, the uh, the code to get this sensor to work. So um, my goal is to use this and to interface it with this uh, this robot. Well, not it's not a robot yet, but I built a frame, put some wheels there using a brass frame here, and then this is L298N motor driven by ST Microelectronics, and I this one is a 5 volt to uh, 12 volts DC to DC buck boost converter. It's actually variable, so I'm actually using these to convert uh, power from battery bank. So I have this one here, and I also have this one here. Um, so I want to use it to build the self-balancing robot. Now, the one limitation that I have, uh, self, and you know, sometimes we tend to have very wishful thinkings and stuff, and it's great to have wishful thinkings, and then you start a project, you start doing more and more research, and start figuring out more and more things about how to interface your project and get it to work. And you start finding out that certain things that you thought of were possible to do might not be so possible to do. Best example is that with these accelerometer readings, as you can see here, it is very, very shaky and responsive, right? So the basic premise of this reading is to figure out the position of your robot. So if you think about it, this microcontroller will be mounted on the robot in a certain orientation. So you can pick like it being this flat, right? And the robot will be standing upright with the two wheels, so it can either swing forward or backward. And so you know if you're looking at the reading there and you swing forward and backward, you can see if 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 the robot, if you put a PID control loop there, so we're looking at the blue signal here, the blue signal here. If you put a PID control loop there and you put a set point and you want it to reach to that set point, you can see yeah, those readings are very friendly there. So came to find out real quickly that because I wanted to use the minimum, although I've already spent quite a bit of time and money uh, trying to get everything together. So I wanted to still spend the least amount of money, or uh, uh, do the least amount to implement this. Uh, uh, so I thought, hey, this one has a accelerometer in there. I might just use this, and that's how I use to control the position of the robot. So you actually need gy- gy- uh, a gyroscope reading, the accelerator meter reading, to actually come up with much cleaner and much nicer positional uh, uh, reading or measurements and stuff of a position to have a better and dynamic control of your robot. based on its position in space. So this was very wishful thinking. I mean, it's a great experience that I actually got it to work, and I got it to interface. Is I learned really a lot. I can take everything that I learned here and use it uh, use it to build a robot that actually have the right sensor, and the right sensor for it is actually uh, this one here. This is uh, the MPU. Let me see again. What is it called again? Okay, this is a Chinese made one and stuff, but this is a gyroscope and accelerometer meter in only one package. So I'm gonna use the experience that I learned here with SPI interface and interface it with this one. This actually use I2C, but it's not too far from SPI. Uh, and implement that, and then we'll see how that goes. But for right now, that's pretty much it. I will end there. Thank you.